Go ahead, do this. Hi, welcome to summertime physics. Yay. I'm going to show you how to do some homework problems from the book. It's number 3, which has to deal with acrobats standing on top of each other's shoulders. Number 5, which has to do with the density of the nucleus of an atom. And then number 21, which deals with absolute pressure at the bottom of a freshwater lake and how much force that pressure exerts on the window of a submarine type thing. All right, so for number 3, we'll start out with that. There are 4 acrobats, and they're all standing on each other's shoulders, and the question is how much pressure is exerted by the feet of the bottom one on the floor. So the first thing we'll do to add up all of their masses, which acrobat number 1 is 75 kgs, the next guy is 68 kgs, the third guy is 62, and that happy guy on the bottom, 55 kgs. Add them all up and you will get 260 kilograms is the mass of all of them. Multiply that by 9.8 because mg is the force of the weight of all of these guys, and so 260 times 9.8 is 2,548 newtons. So 2548 newtons is the force that is applied right there, and you will divide force by area since he's got 2 foots, and the area of each foot was given as 425 square centimeters. Please remember that when you go from centimeters to meters, you know you go 2 spots, but in this case it's squared, so you got to go 2 spots squared, so it's 4 spots, and he's got 2 feet, each with an area of that much square meters. So if you divide 2,548 by, in parentheses, 2 times that quantity, you're going to get 30,000, and that is in pascals, so newtons per square meter. All right, so that one is pretty straightforward. So you got to get the weight of everything and divide that by the surface area that's in contact with the ground. So there's the pressure of this one. Number 5 says, hey, it gives you the mass and the volume of protons and neutrons, and it says using that information pick several of them to clump together to form a nucleus and see what the density of the nucleus is. The formula for density is mass divided by volume. That's pretty easy. What might throw some students off is when it says several. It means you can pick any number, any given number. So as long as it's the mass and the volume of any number of protons and neutrons, then you'll be fine. It'll be the same ratio. So if you say the mass given for any given proton or neutron, 1.67 e negative 27 kgs. Divide that by the volume of one particular proton or neutron. Volume, though, you'll have to do the math to get it because it told you what the radius. And so the volume is 4/3 times pi times that r squared, 10 to the negative 15th, or 10 cubed, I'm sorry, 10 to the negative 15th, and you do have to cube just that number. All right, so when you type it, it might throw you off a little bit, but as long as you have in parentheses 4 divided by 3, then you can just move on to pushing the times button, pi, and I would go times 1 e negative 15. Maybe I should do that. That'll be easier. 1 e negative 15 cubed. The calculator will know to cube just the 1 e negative 15 if you type it with the capital E. If you don't, then it won't do it correctly. All right? But anyway, the mass of 1 divided by the volume of 1. So 1m divided by 1v. So in this case, the number that you're using is simply 1. And this will get you in the neighborhood of 4e17, and that's kilograms per cubic meter. All right? if you pick any other number than 1, as long as you say, okay, how many of those protons? I don't know, 7. Then you'll have to divide it by 7 of those volumes. So you're going to take that ratio and multiply it by 7 and divide it by 7, so it will stay the same. So the density of the nucleus of any given atom will always be the same as each other because they're all made of the same stuff, protons and neutrons. And the, boy, that's a big number. It's much larger than the density of atoms or the density of a certain substance, like in a chemistry class. In iron, the density is like 700, or I'm sorry, about 7,000 kilograms per cubic meter. And that just tells you, hey, atoms are just like life. A whole lot of nothing. All right. Then question 21 dealt with the absolute pressure at the bottom of a lake. So absolute pressure is the pressure that's due to the gauge plus the pressure that's due to the atmosphere. Gauge pressure is rho GH, so it's the density of the fluid you're hanging out the bottom of times G, rho times G times H. H is depth, height or depth, which is kind of confusing, plus atmosphere, which is 101.3 E3 Pascal. So the density in this case of water is 1,000 kilograms per cubic meter. We're going to multiply that by the planet we're hanging out on, 9.8, times the depth that was given in the question is what, 27.5, is that right? Mm-hmm. 27.5 meters. So 9,800 times 27.5 plus 101.3 E3. And what do we get? This is dancing around 26,900, right? 26,900 plus 101, and then you can move the decimal point 3 spots here. 3 1. This is the absolute pressure. Push the plus button, so it'll be a really big number. It's going to be about 3.7 e to the 5th Pascal. So that's the absolute pressure. And so then we know, all right, pressure is force divided by area. So if it wants to know the force that this pressure is exerting on a window of a certain square meter, then all you have to do is just take that pressure and multiply it by area, and that'll give you force. So that becomes force is equal to pressure times area. This is the pressure. The area given that we'll use is what it said the diameter of the window is 35 centimeters. So the area is, or the radius is half of that, so it'll be 17.5, but that's that's centimeters. Turn it into meters means we'll move the decimal point 2 spots that way. So 0.175 meters, and we're going to have to square that number and multiply it by pi. So there's pi r squared times this pressure, 3.7 e to the 5th pascals. And when you do that, you will get something along the lines of, gosh, 3.56, something like that, 3.6 times 10 to the 4th newtons. So 35,600 newtons is the force exerted by the water and the atmosphere when you're at a depth of 27.5 meters. So on a window that is that particular area. All right, I'm going to do 2 more. Question 23 and number 27. 23 is the one that says, hey, if you have an IV solution that happens to be glucose, and we're going to let that solution drip into your vein, well, you know your veins have a certain blood pressure, which I'm sure you've heard of, but in order for stuff to go into a vein, the stuff has to be pushed into it with a greater force, which means a greater pressure. than what is trying to squeeze it out of there, your greater blood pressure. So the whole philosophy in 23 is just say, okay, this pressure has to be greater than the pressure that's inside your arm. All right, the blood vessels in your arm. And then the next one we'll do is 27, which deals with the pressure and the force exerted on brake pads that stops your car. And we'll have to review some topics from Physics 1 in order to answer that. Yay, torque. All right, so for number 23, the first thing I'm going to do is remind you that what we said earlier, a specific gravity of something, and convert that into a density. The specific gravity of this particular item was given as 1.02. And remember, specific gravity is simply the density of something divided by the density of water. Compared to the density of water, this is 1.02 times more dense than water. So if you convert a specific gravity to a density, remember you're just multiplying now by 1,000 rather than dividing by 1,000. So this is the same thing as 1,020 kilograms per cubic meter. All right, so that's specific gravity to density. The density of that glucose solution, a little more dense than water, that makes sense. It's got sugar in it. So then the pressure in the glucose bag has to be greater than what's given in the vein. And so pressure, again, is simply rho, the one we just figured out, times G times H. We're going to solve it for H. And so the pressure given in the problem divided by the density we just figured out times what planet we happen to be on. So this is going to be the blood pressure given is, this was given in the problem, 1.33 times 10 to the third pascals. That's the amount of pressure in the vein trying to push blood through it, or if you poke a hole in it, that's pushing the blood out. Rho, we just got 1020, and that's kilograms per cubic meter, and we'll multiply that by the fact that we're hanging out on planet Earth. Okay, so get all that stuff together, you're going to get an answer that's dancing around 13 centimeters. Your calculator will give it to you in meters, though. I'm sorry, it'd be 0.13 meters, which is 13-ish centimeters. So that's how much higher is the minimum height that an IV has to be above you. If it's glucose, if it's salt, it's got to be a little different based on the density of salt water, a little higher than sugar water. Okay? All right, 27. Oy. 27 talks about the area of a pedal exerted on a brake, then an area of a brake pad itself pushing up against the wheels of a car to stop it. The force that you will physically apply to the brake pedal, then it goes through a hydraulic system and applies another force to the brake pad itself. We're going to figure that out first. That's goal number 1. Then it says, hey, the coefficient of friction between that brake pad and the tire itself, the wheel of the car, is 0.5. Friction is what will stop the car. So the next thing they want to know is, okay, what's the force that that brake pad exerts due to friction on the wheel as it stops it? So that's goal number 2. And then, if you remember from Physics 1, torque. That torque that the brake pad exerts to stop the car is goal number 3. So this one's like a Skinner song. It takes 3 steps. All right? Given in the problem, the area of the pedal itself, the 1.8 square centimeters. I'm not going to mess with converting it because we're going to push the divide button anyway. Those units will cancel out. The force that you will physically apply to that brake pedal is given as 44 newtons. All right? The area that the brake pad pushes up against the wheel of the car is given as 6.4 square centimeters. And so we're going to first use Pascal's principle that says, hey, forces are related as a ratio of areas. Okay? So goal number 1 will be achieved by saying, hey, the force of the pad that you apply to it, or to the pedal, sorry, that you apply to it, divided by the area of the pedal is going to be exactly the same. When you apply a pressure through any given fluid, that pressure is evenly distributed throughout the fluid, so that's going to be the same thing as the force that the brake will apply to the wheel, the brake pad divided by the area that the brake pad, surface area up against it and the wheel. All right? So for this particular one, we're solving for force that the brake exerts, so all I got to do is multiply that over, so it'll be a force of the pedal times the area of the brake pad divided by the area of the pedal. So the forces are multiplied according to a ratio of the areas. This force, 44 newtons, times the area of the brake now, 6.4 square centimeters divided by the area of the pedal, which was 1.8 square centimeters, and that's why I didn't mess with converting it, because the units die anyway. So you see that force is multiplied according to a ratio of their areas. So the force that the brake is exerting, 44 times 6.4 divided by 1.8, that is 156 newtons. So goal number 1 has been achieved. That's the force that the brake pad exerts on the wheel itself. Okay? Now, that's simply a normal force. When a brake pad pushes up against a wheel, it pushes perpendicularly. To get the force of friction, then, we'll have to remind ourselves from Physics 1, the force of friction is equal to mu times a normal force. A normal force is anything that acts perpendicularly. Since the brake pad pushes perpendicularly against the surface of the wheel of the car, that Fn is what we just calculated as goal number 1. It's 156 newtons. So the force of friction is simply mu Fn. The mu is given as 0.5 times 156. So it's just a half of 156 newtons. So the force of friction exerted by the brake pad against the wheel is 78 newtons. All right, so goal number 2 has been achieved, the force of friction, and then the torque that it will apply to the wheel. Again, to remind yourself from Physics 1, torque is a force times a radius, or the distance that that force is being applied around the axis of rotation of whatever is rotating. So in this case, you know, a car tire has an axle, and the brake pads are exerted a certain distance from that axle. So that distance is going to be a radius. We'll multiply that by 78 newtons. So the torque that is exerted by the brake pad is its force, 78 newtons, the force of friction, or the torque due to friction, times the radius of the tire, which was given as what was it given? It was given as 0.34 meters, so it's about a foot, 34 centimeters, that's ish a foot. And so the torque that stops your car is about a third-ish of 78. It turns out to be 27 Newton meters. Huh? Huh? All right, so that was a quick overview of those. I'll post a few more as the summertime progresses. Feel free to email me with any other questions, and yay, physics!